OK, we're halfway done with the handshake. I told you it was kind of long. So at this point, regardless of which step 3 you chose, whether you chose the Diffie-Hellman version or the RSA version, there is now a secret that the client knows and the server knows and nobody else knows. You're at that point. So once the client and the server have a secret key that nobody else knows, they can use that one secret to derive more secret keys. So what they'll do is they'll take that shared secret, PS, pre-master secret, and they'll also take the 2 random values from earlier to throw in some extra randomness to make sure that every handshake is different. We'll take these 3 values, we'll throw them into some PRNG soup or some hash, and out comes 4 different keys for encrypting and macking. Now, why it's 4 is kind of a footnote. So for now, if you want to just think of it as a bunch of keys they can use for encrypting and macking, that's fine. But formally, it's 4 keys. 1 key for encrypting in this direction, 1 key for encrypting in this direction, 1 key for macking in the client to server direction, 1 key for macking in the server to client direction. We'll revisit that in a little bit, but for now, you're deriving a bunch of keys based on 1 key. And remember, this is done offline, so at no point do you send the actual keys across the channel, because then you would leak the keys. So instead, both of them do this on their own independently using some deterministic algorithm. And as long as you pass in the same inputs on both sides, you should get the same resulting keys. So at this point, both the client and the server have a bunch of keys that they can use for encrypting their messages and macking their messages, but we're not quite done. So far, a lot of data has been sent back and forth. There was a Diffie-Hellman key exchange or an RSA message. There were those random values from earlier. There was a certificate. How do the client and the server know that none of these values have been tampered with? What if an attacker came along earlier and swapped the random value up here? We have to catch that somehow. Or what if an attacker came and swapped this value right here? We have to catch that. So the way we're going to catch it before we're totally done is to use MACs, and these are message authentication codes between the client and the server, just to double check that everything we've sent so far is correct. Now, how this exactly works is not the most important thing. If you remember MACs and you just trust that MACs do the right thing and they give us integrity, then you can just see this and say, sure, both of them compute MACs. Therefore, if any of the earlier messages were tampered with, you will catch it here. So if you just trust that MACs provide integrity, you can look at this slide and say, MACs provide integrity. Nobody can tamper with steps 1 through 4. If you want to be more precise, what really happens is that the client computes a MAC and then sends it of everything they've sent and received, sends it to the server, and then the server recomputes the MAC to see if they get the same value. And if any of the values were tampered with, then the client would feed in 1 value into the MAC, the server would feed a different value into the MAC, they would not be the same, and they would derive a different MAC from what they computed. Once again, if you just trust that MACs are correct, you don't have to listen to any of this, but if you're really paranoid or you want to know how it works, it might look something like that. The client writes down every single value they've ever sent and received in this handshake, they compute a MAC on it and send it to the server. And then the server does the same thing. They write down every single value they've sent or received. They compute a MAC as well using the same key. If nothing was tampered with, then everything you sent and received should be the same. You both will get the same MAC. So the server receives a MAC, computes a MAC. They're the same value. Everything is good. However, if something was tampered with, then the client would have received one version, and the server would have sent something different. That's what it means for tampering to happen. The server sends one value, and the client receives a different value. So in that case, when the client computes a MAC, they would compute it using the wrong input and sends it over to the server. And when the server computes the MAC, they would compute it using a different input. The MACs would be different, and the server can detect tampering occurring. So in case you're really curious, that's how it works. But when you're looking at this handshake, it's OK to just think MACs provide integrity, so this does what MACs are supposed to do. OK, finally we are done. We have a set of secret keys that nobody else knows. There's different keys for encrypting than macking, so we don't have to worry about key reuse. And we've also added a MAC step to make sure that no tampering has occurred during the handshake. So we're finally done. And at this point, you're ready to send messages. You can encrypt them using your encryption keys. You can MAC them using the MAC keys. And now your messages are protected with confidentiality and integrity as they are sent across the network. And that's the end of the handshake. Everything after this would be exchanging data.